So last time we started with the following example. We have a conduction diffusive problem. They imposed on us the values of the variable at x equals 0 and x equal L, and they want us to solve for different cases. For a velocity of 0.1 meter per second first, then a velocity of 2.5 meter per second. So we are using the same grid for both cases. We are using first 5 grid points, if you remember. And we said that if we have 5 grid points, we have 5 cells, and then we have to write for each cell the equation. We have for cell 1 and cell 5, we need to take into account the boundary condition, and the form of equation for 2, 3, and 4 is the same. So you can derive just the equation of cell 1, the equation of cell 5, and one equation function of I, which is the number of cells for 2, 3, and 4. Once you do this, you can have the coefficients, okay, for each equation. So as you can see here, you can summarize your findings in a table where you show the coefficient of P, the coefficient of west, east, and the source term. Here, for example, the notation they are using in these examples are a little bit different than the notation we are using, but it doesn't matter. انتوا فيكم تسموا الكوفيشنت مثل ما بدكم. يعني نحن سوا كنا مسميينهم كنا حاطينهم from same side. يعني إذا بتتذكروا نحن كيف كنا مسميين الايكويشن like this. AP phi P plus A west phi west plus A east phi east equals to a source term. هن بس غيروا شوي انه يعني هن اخدين الويست coefficient والايست coefficient لتاني مال. It's fine. يعني just هن بيطلع لهم ال A تبعهم هن minus ال A تبعنا. بس it's the same. At the end you have the same result. When you solve you get the same result. So A east phi east equal to نحن كنا ناخد BP. هن هون مسميين الsource term SU. Okay? And now once you write the equations for the different cells, you will be able to summarize your results in a table. And after you have the coefficients, okay, you can then transform the equation to a matrix form. يعني by replacing the coefficients that we have. هون رجعوا أخذون لتاني مال أكيد. يعني at the end you should take them again to the other side. فيطلع لنا هون matrix of coefficient of all variables, and بتخلوا على right side the source term. Okay. Now how to solve such system? Here you have several methods. هلا أكيد أنا بالإكزام إذا بدي أعطيكم شيء to solve ما بعطيكم أكثر من إذا عندي matrix 3 by 3 بتعرفوا تحلوها بالكالكوليتر. Your calculator can solve up to 3 by 3. The purpose is not to solve, you know how to solve such systems بالnumerical methods. يعني في Jacobian method, Gaussian method. You already know these techniques from other courses. The purpose is to reach this state. يعني أنا بيهمني تقدروا تكتبوا الماتريكس, and then as solution you are responsible only of the TDMA لأنه هوليك methods you know them from other courses. So you can use the TDMA method. We developed together the TDMA method in the course material. You just have to apply it. هلا we'll do problems, additional problems on TDMA after. Okay. Now, once we do this step, the second step will be to compare with the analytical solution to see the accuracy of our solution. In this problem, they gave us the analytical solution. So we can compute the actual value of pi at the different nodes. So we know that delta x is given 0.2. So for the first point, x1 is 0.2 over 2 is 0.1. And then you add 0.2. So for the second node, 0.1 plus 0.2 will give you x2 equal to 0.3, etc. So you have coordinates of your 5 points. Once you have them, you just have to replace into the function here. and get the actual value of phi x. And since you have already computed numerically using the finite volume technique, the values of phi at the nodes, you can compare. You can see the difference and calculate the percentage of error. The percentage of error is the difference over the analytical solution. It seems here that the computation is good. The maximum error you obtained is around 5%, which is acceptable. It's fine. So the use of, in this case, we use the central difference scheme. The central differencing scheme worked well for relatively small velocity. Now, in case 2, they asked us to increase the velocity. And here, you have u relatively small. And to assess if you want the effect of convection relative to conduction, we can calculate the Pecklet number. The Pecklet number, as we have seen last time, will relate is like a ratio of convection over diffusion. So larger the Pecklet number, more dominant will be the convection. For u equal to 0.1, we have relatively small Pecklet number, and this will explain the good performance of the central difference scheme. However, if we increase the velocity and we keep the grid as it is, so if we work now in case 2, we'll do the same work, but now we will take a larger velocity. And exactly same procedure, same equations, but now with larger velocity, we can compute for this velocity the value of coefficients, and then we can write our matrix and solve for it. Then we can find the finite volume solution and compare it with the analytical solution. If you find now the difference and find the percentage error, the error is really very high. You can reach up to an error of 168.48%, 170% nearly, which is really high. And how we can explain this? We know that the central difference scheme works well whenever conduction is dominant. As the convective term becomes dominant, the upwind scheme will perform better. Why? Because we said that when we take the central difference scheme, we consider that you have linear variation between of the variable between 2 nodes. While in case of convection, the value of, when you have dominant convection, the value of the variable here will be much more affected by the value before it, if u is positive, than by the variable value after it. While if u is negative, it will be more affected by the value here. And the central difference scheme cannot capture this because it will do a linear interpolation between these 2 points. While the upwind scheme will take into consideration the flow direction and its effect on computation. So as you can see here, the solution is really bad. Hatta the profile is not, you have oscillating results. The profile is not good at all. And we have divergence if you want. We cannot consider that it is a good solution. To try to understand this and to say in which cases the central difference scheme is good and in which cases the upwind scheme is better, we will do a small analysis based on the Pecklet number to decide, based on this dimensionless number, when to use the upwind scheme and when to use the central difference. Now, a possible solution for this, okay, will be to increase the number of grid points. And we'll see together why it will be a good strategy to increase the number of grid points. So now, if you repeat the same procedure, but now instead of taking 5 nodes, you take 20 nodes, okay? Then you will see that even if you use the central difference scheme, it will work well. Why? To understand why, because when you take smaller distances, then the Pecklet number will be reduced, even if you have same u. Okay, now we'll see together what is the Pecklet number and how we can justify that the Pecklet number for small value of Pecklet number central difference scheme will work well, while for larger value, it will not work well. So here, if we do for the same velocity, which is the high velocity of 2.5 meters per second, if we just increase the number of nodes, even if we use the central difference scheme, it will still work. Okay, so now if you repeat the work for much more higher number of nodes, the numerical solution will be very close to the exact solution, and the error, the percentage error, will be much reduced. Okay, now what we want to do, we want to do the analysis of this, why this is happening. To understand why this is happening, we'll go back to the course material. We have already derived together expressions for the upwind scheme and expressions for the central scheme. And if we look at the stability criterion that we already covered together, okay, we have seen that to say that a certain scheme is stable, one strategy will be to derive the right-hand side with respect to phi p, and we should get a negative result. So we have seen that for diffusion, we always get a negative result. This is why for the case of pure diffusion, your system, your equation is stable, and in general, you don't have a problem. Now, whenever you have convection, to account for convection, or you can use the central scheme, or you can use the upwind scheme. The upwind scheme was shown to be more stable because when you derive the right-hand side of the upwind term, you get a negative result. However, for the central scheme, you get a result close to zero, which means that the central scheme is unstable. Now, what is the strategy to enhance, if you want, the performance of the central scheme? The idea is the following. Let us do a hybrid scheme. The hybrid scheme will combine the central and upwind scheme in order to add to have a more robust model. Okay, and in this case, when ليش نحن بنحب السنترال scheme? The central scheme has advantage إنه accuracy تبعه يعني when it will work well, it is more accurate than the upwind scheme. But for large Pecklet number, it will not work well. So this is why we will say if the Pecklet number is small, then we'll use the central scheme. If the Pecklet number is large, we'll use the upwind scheme. How we define the Pecklet number? From our when you put your coefficients, okay? Let us take the case of, let's say you have convection in the positive direction. You have U positive, so U is moving like this. We can develop together for any velocity, for any cell, as we did last time. We can develop the expressions of coefficients. So when you look at your coefficients, you have the following. In case you have a central scheme and you take U positive, then your east coefficient will be given by minus tau delta y over delta x east plus rho U delta y over 2. A west is minus tau delta y over delta x minus rho U delta y over 2. And AP is tau delta y east over delta x east plus tau delta y over delta x west plus rho U delta y over 2 east minus rho U delta y over 2 west. هيدا عملنا لهم demonstration last time. Okay? Now, if we do the criteria of stability, from your criteria of stability, if you remember, when we do the derivative here with respect to phi, we have seen that the condition of stability is to get here a negative result. When we derive the right-hand side with respect to phi p, we should get a negative result. So our coefficient should be a negative. Okay. Now, if you look at this expression, the coefficient A at east is equal to minus tau delta y over delta x plus rho U delta y east over 2. The condition of stability is that this term, so to have stable solution, this term should be negative. However, this will not always be the case. What is the condition to have a negative coefficient? You should have rho times U times delta y east over 2 should be smaller than the diffusivity coefficient. And I will take this term to the other side. Should be smaller than the diffusivity coefficient times delta y east over delta x east. Now, if you simplify delta y east, okay, you can say that, and if you take these terms, tau and delta x to the other side, you get the following condition. You should have rho times u times delta x at east over the diffusivity coefficient tau should be smaller than 2. This is the condition to have stable solution. And this is what we call the Pecklet number. This is the dimensionless number that we call Pecklet number. As you can see, it represents the ratio of convection to diffusion effect, because the convective effect is present in the numerator as rho u times the grid size over the diffusivity. If we do a small analysis, how we can reduce the Pecklet number when we do computation? نحن مجبورين بالu. Rho u, we cannot play with it. And the diffusivity also, it depends on the problem we have. But we can play with what? With the grid size. Yes, exactly. So we can, when we decrease the grid size, yani by increasing the number of nodes, we will be able to decrease the Pecklet number. To have a stable solution with the central scheme, I should go below 2. Okay, if I can't go below 2, then my central scheme will not work well. Of course, we have a limit in decreasing delta x, and if I decrease delta x a lot, I will have increased computational time. So this is why the advantage of the hybrid scheme is that I can consider for any cell, I calculate the Pecklet number. If the Pecklet number is smaller than 2, I use the central scheme in this cell to approximate, if you want, the variation of my variable phi. And in case I have a Pecklet number larger than 2, I use the upwind scheme. In this way, I will take advantages of both schemes. The central scheme performs better for small Pecklet numbers, while the upwind scheme performs better for large Pecklet numbers. And then I can combine the stability of upwind scheme with the accuracy of central scheme when I solve. Okay, so this is the strategy. As you can see, with upwind scheme, your coefficients are negative, so you are it's fine for you. You have stable solution. While for the central scheme, you have a condition. The condition is that to have a negative is that the Pecklet number should be a west and a east. So already a west is negative for the case of positive velocity, so your constraint will just be on a east. The condition is that the Pecklet number should be larger, smaller than 2. You can verify also if u is negative, you have same condition. If u is negative, the condition to have stability of the central scheme is to get that the Pecklet number of the cell is smaller than 2. Okay, but instead of dealing with delta x east, we deal with delta x west, لأنه بيصير بالcoefficients بيقلب هون، هيدي بتصير minus وهيدي يعني بيقلب الساينز. Okay, and you have different coefficients because then this is affected by the flow direction. نحن last time we derived what will be the coefficient if u is positive and what will be the coefficients if u is negative. Now, so this is the definition of the hybrid scheme. The hybrid scheme will take the expression for u positive. It will take this expression for a east when Pecklet number is negative, and in case Pecklet number when Pecklet number is smaller than 2, if Pecklet number is larger than 2, then I use the upwind scheme, and in the upwind scheme, a east will be minus diffusivity coefficient times delta y east over delta x east. And this similarly for A west, in case Becklet number is smaller than 2, then I take coefficient of central scheme, while for while if P Becklet number at west is larger than 2, I use the formulation of upwind scheme. And in this way, I will have a good scheme that can give me combine the stability effect of upwind scheme and the accuracy of central scheme. Okay, so as you can see here, we can observe that larger the Becklet number, lower will be the performance. of course the hybrid scheme بعده احسن بكتير من انه استعمل السنترال لحاله. بالسنترال لحاله بس كتير يعلى الباكلت نمبر، شفنا كيف بتصير السوليوشن، بيصير في a lot of oscillations. Okay, so whenever I use the hybrid scheme, still I have error, but this error is acceptable. I can still compute an accurate profile. To enhance the accuracy, I can increase the number of nodes. Yani always increasing the number of nodes will is expected to give me better results. Okay. Now, so we can observe this using the example we did. We already have seen these properties together. We have considered the first central scheme for small Becklet number. It was very accurate here because the velocity was really small. Now, when we increase the velocity, if you calculate the Becklet number, هيبين معكم هون the Becklet number is larger than 2, which explains the bad results given by the central difference scheme. And when you, for the same velocity, when you decrease delta x, you will be able to reach Becklet number smaller than 2, which explains then the good behavior of the numerical method. مع انه بعدنا عم نستعمل central difference، بس الفرق انه when we decrease the size delta x, then we're able to have accurate solution because the Becklet number was reduced below 2. So, as interpretation, we can say that the agreement between the numerical results and the analytical solution is good when we increase the number of grid points. Comparison of the data for this case with the one computed on the 5-point grid of case 2 shows that grid refinement has reduced the ratio F over D يلي هو related هو Becklet number related Becklet number from 5 to 1.25. So the central difference scheme seems to yield accurate results when the ratio F over D is low. يعني هون عم يعملوا interpretation قبل ما يعملوا الاناليسيس اللي عملناها انا وياكم. نحن هلا صرنا نعرف انه Becklet number smaller than 2 will give good prediction بالcentral scheme, while for value larger than 2 بيكون عندنا bad results. So the influence of F over D ratio and the reasons for the appearance of wiggles in central difference solution will be discussed. نحن عملنا discussion وشفنا انه it's due to the stability اللي هي related للcoefficient. إذا coefficient negative we have a stable solution. إذا coefficient positive we have unstable solution. One of the major bad effects of the central difference scheme is its inability to identify flow direction. مثل ما قلنا central difference scheme بياخد linear interpolation. So بس يكون عندنا dominant convection, it will not perform well because in dominant convection the value at the node here will be affected more by the value that is convected by the flow. So the value of property phi at west cell face is always influenced by both phi p and phi w in central differencing scheme. However, if we have a strongly convective flow from west to east, the above treatment is not convenient because the west cell face should receive much stronger influence from node of west than from the node at east of P. The upwind differencing or donor cell، نحن بنسمي الupwind donor cell لأنه بيتأثر بالبارت اللي in the direction of the flow اللي جاي منها الفلو. Takes into account the flow direction when finding the value at the cell face. So this is why when convection is dominant, the upwind scheme will perform better لأنه بيكون الباكلت number larger than 2 in this case. Now we can see this again in another example. So now they want us to solve the same problem, but now using the upwind differencing scheme. Also for two velocities, 0.1 meter per second and 2.5 meter per second, and both for course 5-point grid. يعني هناخد الجريد الكريتيكال اللي هي small number of points. هنشوف انه لو عندنا small number of points, the upwind scheme will perform well لانه upwind scheme بيشتغل منيح for large packlet number, while central difference scheme will not work well for large packlet numbers. So here also same procedure. I start by writing the equation for each cell. نحن already أنا وياكم كتبنا equation last time. And now when we want to compute phi at east face or west face, then we should, instead of using central scheme, هنستعمل the upwind differencing scheme. يعني whenever we want to replace phi at east face, so this is a face, عندنا الإيست عندنا الويست فيس وعندنا الإيست فيس وعندنا السنتر نود بنسميه phi p. We have phi at p and we have phi west, phi big W, and phi here big E. Now if we have positive velocity, okay, then when we want to compute phi west, شو بنحطها بالupwind scheme? So for U positive بالupwind scheme, we replace phi at west face by what? إذا الفلو جاي هيك, okay? What is the value which will be transported towards the face at west? يلا, who can answer me? No answer?
Phi west.
Yes, phi west. Okay. And if I want to compute phi at east face, I will put what?
Phi p.
Very good, phi p. لو كانت عندنا velocity negative, if the velocity was negative in the other direction, ساعتها if U negative, what do I take? If U negative, phi west شو بتكون؟
بتكون phi p.
Exactly. Yes. And phi east بتكون
Phi east.
Okay, very good. So here, because U is positive, I will take the first scenario and then I can develop my equations and find my coefficients. Once I find my coefficients, I can write my matrix and solve for it. Okay. ساعتها, once I have the values obtained from finite volume solution, I can compare with the analytical solution. هتشوفوا هون إنه الerror, the percentage error is good. Okay. عندي الerror أصغر بعد من الcentral scheme لأنه هون convection is important in this case. So هلا هونيك الcentral difference scheme كمان اشتغل منيح لأنه الباكلت number was smaller than. اوكي, بس هو منه كتير صغير هون الباكلت number. كل ما صغر أكتر كل ما السنترال سكيم بيصير more accurate من الابويند. كل ما قرب على 2 كل ما يصير الابويند performance, upwind scheme performance relatively better. Okay, so now next step we'll repeat the same calculation but for U equal to 2.5 meters per second. For U equal to 2.5 meters per second, هونيك طلع عنا error كتير كبيرة بالcentral scheme. طلعت of the order of 170%. بينما when we used the upwind scheme, the percent of error was relatively much more acceptable. يعني مظبوط بعد في error بس انه 22% احسن بكتير من 170%. So what we can say is that even with a coarse grid, even with a small number of cells, the upwind scheme is able to give good predictions for large Becklet numbers. We can still enhance this solution. Of course, to enhance this solution, we can increase the number of points, so we can reduce our grid size. Okay. So now, if you solve this problem with 25 nodes, okay, but they want you to use the hybrid scheme, you will use the hybrid scheme. So when you have if you want a small Becklet number, you use central scheme, and when you have high Becklet number, you use the upwind scheme. Okay. Here, for example, تتعرفوا شو نعمل؟ بدنا نعمل calculation للباكلت number. here in this problem بما انه عندنا U constant والconductivity constant، يعني ما حتفرق من سيل لسيل الباكلت number. اي متى بتفرق؟ اذا عندي for example variation of velocity within the domain، او عندي variation of diffusivity او variation of density، ساعتها او delta x is not uniform. If I have a non-uniform grid, delta x can change. Okay. So انتم بتشوفوا البروبلم، اذا في problem the Becklet number is varying for different phases، ساعتها على كل phase لازم تعملوا calculation للباكلت number وتحددوا اذا هو smaller than 2 or larger than 2 to decide if I will use this at this phase central scheme او upwind scheme. Okay. هون we don't have this challenge لانه U constant everywhere, delta x is the same because we have a uniform grid, diffusivity is the same. So هون Becklet number is same everywhere. يعني it's enough انه at the beginning of the problem to calculate the value of the Becklet number. بيطلع لنا Becklet number 5. So we can say then we should use the upwind scheme for all my phases. Okay, to compute the coefficients and for all my phases, I will use the upwind scheme because the Becklet number is larger than 2 everywhere. يعني هون الهايبريد scheme هيعطيني exactly same result للupwind scheme. Okay. While if I have change of Becklet number, sometimes it's smaller than 2 for some phases, for other phases larger than 2. ساعتها I apply for phases smaller than 2 central difference scheme, and for phases characterized by Becklet number larger than 2, I apply the upwind scheme. Okay. هون حنشوف انه اذا بنزيد number of grid points تتحسن البرفورمانس بالupwind كمان. يعني if you compare now with the solution, look, you have a much better result. Okay. So you have a very good computation by increasing the number of cells. Okay. So this is the chapter of diffusion convection schemes. So you have in summary, okay, in summary, you have several methods to deal with problems of convection diffusion. You can use central difference scheme, you can use upwind scheme, and you can use the hybrid scheme. When Becklet number is smaller than 2, it's better to use the central scheme. When Becklet number is larger than 2, then we use the upwind scheme. Okay. Any question on this? Okay. So we'll continue now with some extra problems. Yes.
أنا عندي سؤال صغير. قلت لنا إنه ننتبه على الباكلت نمبر لكل سيل حتى لي نعرف إذا بدنا نشتغل
صح. مش بس لكل سيل، لكل فيس شربل، لكل فيس. لأنه أنت الباكلت نمبر إذا بتلاحظ الإكسبريشن تبعه هو رو يو at a certain phase. يعني أنت تنقول هلا أنت وقت تطلع الإكسبريشن of your fluxes عندك phi at east west phase وعندك phi at east phase. أوكي. طيب هلا أنت when you want to replace بالإكويشن تبعك what is phi at west، بدك تقرر أي سكيم تستعمل upwind أو central. فأنت الباكلت number you calculate it at the face. يعني إذا بدي أعرف phi west at west face بشو بدي أعمل لها replacement، I should calculate باكلت number at west face اللي هو rho times u at west face يعني ال velocity of flow يلي passing through this face times delta x west. delta x west هي الديستنس بين السنتر يعني هيدا البوينت W هيدا البوينت P. delta x west is this distance, the distance between point W and P. This is delta x west. هلا إذا عندك uniform grid ما بيعود يفرق لأنه بيصير delta x west equal delta x east equal to delta x of the cell. بس in case you have non-uniform grid ساعتها هيدا الترم بس بدك تاخد الويست face بدك تاخد distance from point W to point P. اوكي over الديفيوزيفيتي coefficient على الويست face. هلا هون كمان it depends إذا عندي constant diffusivity بتكون هي ذاتها everywhere. if not تتذكروا كيف عملنا harmonic interpolation تنجيب ال value of diffusivity at a face. ساعتها بتستعمل harmonic interpolation to get this. اوكي فكل ما بتشتغل على face انت كل face بدك تعمل replacement لفاي بالايكويشن you will replace phi at west and you will replace phi at east. فتعرف اي scheme to use to replace phi at west بدك تجيب الباكلت number at west وتتعرف اي scheme you should use to replace phi at east you should calculate packlet number at east face. هلا if you have that the packlet number at west face is smaller than 2 ساعتها بتقول انه phi west can be computed from just doing السنترال scheme. شو السنترال scheme؟ يعني باخد phi at west plus phi at p over 2 هيدا السنترال scheme. واذا طلع لي الباكلت نمبر على هيدي الفيس اكبر من 2 ساعتها بقول لا بدي استعمل الابويند scheme. So for packlet number larger than 2 I replace phi west by phi west face by phi at point W big W. Okay?
اوكي دكتور وضحت.
Any other question?
وانا
دكتور
بعرف
دلتا اكس
نعم.
حتى لو كانت upwind scheme هي من البوينت W على البوينت B صح؟
الدلتا يس اكيد الدلتا اكس ما خاصه اذا عندي upwind scheme او central difference scheme. دلتا هيدي الدلتا اكس ويست هي الديستنس بين بوينت W والبوينت B. ودلتا اكس ايست هيدي دلتا اكس ايست هي الديستنس بين بوينت بي وبوينت بيج اي. اوكي هلا اذا كانت يونيفورم جريد ساعتها هيدي الديستنس بتكون ايكوال لهيدي بتكون ايكوال لدلتا اكس اللي هي اللينث اوف ذا سيل دلتا اكس. بينما اذا عندي نون يونيفورم جريد بصيروا ديفرنت فاليوز.
اوكي دكتور.
اوكي لانه بتصير دلتا اكس بتصير دلتا اكس دبليو اوفر 2 plus delta x east over 2. Okay?
Yes.
Clear? Any other question on this?
دكتور بس للتأكيد إنه حتى شوي صوتي لما تكون بيكلس نمبر أصغر من 2 بستعمل هايبريد.
إذا باكلت نمبر أصغر من 2 مش قصة تستعمل الهايبريد، قصة أنت عادة الهايبريد سكيم is a good strategy بس يكون كل فيس بعمل عليها باكلت نمبر. إذا باكلت نمبر أصغر من 2 بستعمل سنترال سكيم، إذا باكلت نمبر larger than 2 بستعمل هايبريد سكيم. أوكي؟ Any other question?
دكتور لو تغير الباكلت نمبر بين سيل وسيل بتتغير الدلتا اكس بتتغير اليو ما هي اليو بتصير بدك تعطيني
انا
اياها بكل
الباكلت
فيس.
نمبر معقول كثير يتغير من فيس لفيس. اذا عندي مثلا اذا حيلا حدا من البارامترز is changing يعني او الديفيوزيفيتي او الفيلوسيتي او let's say السايز اوف يعني اذا ما عندي يونيفورم جريد سايز دلتا اكس بتتغير يعني على كل فيس اذا فاريبل وحده بتتغير معقول الباكلت نمبر يغير. فيكون الباكلت نمبر سيم everywhere مفروض انه كل الفاريبلز تبعي ما يتغيروا او بده يكونوا الكومبينيشن تبعهم ما تتغير. اوكي